So in this lecture we will discuss about the monotone convergence theorem. Which is a very important statement which will be used many times later. So let me state the theorem. It says the following: consider a sequence Fn of non-negative measures, functions. Assume that these functions converge monotonically to a function f. Of course, I'm assuming that these functions Fn are all measurable and that we are working on a measurable space omega f mu. Then the claim is that the integrals of Fn d mu converge to the integral of f d mu. Observe that we are not assuming at any moment that these integrals are finite or this one is finite. We are just assuming that Fn are non-negative and they are increasing to this function f, and the theorem then states that the integrals of Fn will converge to f. So, and we will see that this is a very important result. So, let's go to the proof. Well, f, it's certainly measurable because it's the limit of a sequence of measurable functions. It's positive, so we know that its integral, being positive, it's given by the limit of a sequence of simple functions. And the same thing is true for the functions fg. So here is my function f1, here is f2, and so on. So maybe let me write it f3, and so on. And these functions are increasing to the function f. f1, it's a non-negative function, so its integral, it's given as the limit of the integrals of simple functions which are increasing to f1. So let me represent these simple functions by g11, g12, g13, and so on. So g11, g12, g13, g1n are simple functions which are non-negative and which are increasing to f1. So I will represent that just by saying that, well, in the line, if I follow the line, I have an increasing sequence of simple functions which are increasing to f1. And so that f1 d mu, it's equal to the limit in k of the integral of g1 k d mu. And, well, in the same way, f2, it's a non-negative function, therefore its integral, it's the limit of a sequence of simple functions which are increasing to f2. So let me represent by g21, g22, g23, and so on, a sequence which is increasing to f2 and which is formed by simple functions. So let me again represent that by this symbol, and we can repeat that for each line. So getting here a sequence g31, g32, g33, which are simple functions which are increasing to f3. So along the line I have monotone sequences, and here on this column I have also a sequence of a monotone sequence converging, increasing to f. So this is true for 1, but it's also true for any fixed n. So let me just rewrite that as saying that for any function n, the integral of fn, it's in fact equal to the integral of the limit of the integral of these functions. Right. And what I want to do is to use these simple functions in order to construct a sequence of simple functions which increase to f so that I will be able to represent the integral of f as a function, an integral of a function of these functions, a combination of these functions. So the idea will be the following. I will construct a new sequence, which I will represent by gk. And here is the construction. G1 will be simply the function G11. Then the next function should be larger than G11. I would be tempted to choose G22, but I have no relation between G22 and G11 because they belong to different lines. So what we will do is take the maximum between G12 and G22. In this way, I know that this maximum is larger than G12, which is larger than G11. So I get a function which is larger than the first one. And for the third function, I will just take the maximum between these three functions. So again, this function is larger than that one. This one is larger than that one. Therefore, the maximum of this column, it's larger than the maximum of this column. So in this way, what we are defining as gk, it's a maximum. So we are taking a maximum. So we are fixing the kth column, and we are taking the maximum of the first k terms. So this is a maximum between n from 1 to k of g and k. And now I have to show many things. I have to show that gk are simple functions, that they are increasing, so that the sequence is monotone and it's increasing, and what I want to show that it's increasing in fact to the function f. So that the function is simple, that's very easy because gk it's a maximum over a finite number of functions, of simple functions. So it's very easy to show that a maximum over a finite set of simple functions, it's a simple function. Now I want to show that gk it's monotone, in the sense that gk it's greater or equal than gk it's less than or equal to gk plus 1. But that's very easy because gk plus 1 by definition it's the maximum from n. I will write that in this way. It's the maximum from n from 1 to k of g n k plus 1, maximum the last term. So we have here k plus 1 term. I'm separating the first k and then adding the last one, which is gk plus 1, gk plus 1. Right? Well, now if you fix a line, so if you fix n, on the second variable, so on moving the column, we have a monotone sequence. So this means that gnk plus 1, it's larger or equal than gnk. Right? If I fix a line, and along the line, we have seen that along the line, these sequences are increasing. So this means that for any n, gnk, it's less than or equal to gnk plus 1. Therefore, the maximum is less than or equal to this maximum. And of course, I can just ignore the last term. And this is exactly the definition of gk. So this shows that indeed the sequence gk it's increasing. So it's a sequence of simple functions which are increasing. Now I want to show that it increases to the function f. Well, so what I claim is that if you consider the function gk, right, so gk is the maximum over the first k column. So each, what I want first to claim is that gk is less than or equal to fk. Right? Because, well, that's very easy, because if you fix k, g n k, so let me take n smaller than k, g n k, so if you consider the sequence gn1, gn2, and so on, these sequences are increasing and they increase to fn. So this means that for any fixed n smaller than k, gnk it's less or equal than fn. But the sequence fn, it's monotone. This means that since n is less or equal than k, fn it's less or equal than fk. So maybe let me repeat that. So along the lines, these sequences are increasing to the function f. So the first line is increasing to f1, the second line is increasing to f2, and so on. So this means that if I fix a line, so let's say fix a line n, and consider k larger than n, on this line, the sequence gn, it's increasing to fn, therefore for any k, for any j, gnj, it's smaller than fn. So in particular, if I take k, gnk is smaller than fn. And now if I take n smaller than k, since the sequence fn it's increasing itself, fn is smaller than fk. So this shows you that gnk is smaller than fk for any n smaller than k, and therefore the maximum over n between 1 and k, it's smaller than fk. So this proves this inequality. So gk, it's smaller than fk. And now what I claim is that if I fix n, fix maybe not to mix, fix some integer m, if I take a k larger than m, then since gk is the maximum over all n between 1 and k, gk is certainly larger than gmk. So this is true for any fixed k. So on the one hand, this sequence, as k increases to infinity, it's converging to f. On the other hand, if I fix I send k to infinity, so the limit of gk is an increasing sequence, therefore it has a limit, so let me represent it by g. It's what we obtain from that is that the limit of the sequence gk, it's larger than gmk for any m smaller or equal than k. So now if I fix n and I send k to infinity, so what I'm doing here is that I'm fixing a line and I'm sending the column to infinity, that this sequence here, it's converging to fk. So this shows that the limit of the sequence gk should be larger or equal than fk for any k. Now if I send k to infinity, what I get, I'm sorry, this is m, right? So let me come back. What we have is that gk, which is a maximum from n from 1 to k, it's larger than gmk for any m less than or equal to k. So if I fix m and I send k to infinity, since I'm fixing the line and I'm taking the column to infinity, what I'm taking is a limit on the line, and the limit on the line, it's equal to the line, which is fm. So if I send k to infinity here, this sequence is converging to fm, and therefore fm should be less than or equal to the limit of gk, which I'm representing by g. So I have that inequality, and I have this inequality. Well, if this inequality are correct for any m, if I send now m to infinity, since fm is increasing to f, what I get is that g should be equal to f, and therefore that the sequence gk is in fact converging monotonically to the function f, which is what I wanted to show. So up to this point, I defined this sequence gk, and I proved that this sequence gk is formed of simple functions which are increasing to the function f. Therefore, the integral of f d mu is equal, so remember that if a function f is non-negative, its integral is defined as the limit of a sequence of simple functions. This is the limit as k goes to infinity of the integral of gk d mu. Well, but what do we know? We know that fn, it's increasing to f. Since fn is increasing to f, this means that fn is less than or equal to f, and therefore that the integral of fn it's less than or equal to the integral of f d mu. Since this is true for any n, we have that the limit sup of fn d mu it's less than or equal to f. So therefore, to prove that fn, the integrals of fn are converging to f, what we need to prove is the reverse inequality. So we need an upper bound on the integral of f. So we have to show that this integral is smaller than the limit of fn d mu. So this is the difficult point in the proof. The other one, it's a simple consequence of the fact that fn is less than or equal to f. Well, so we need an upper bound for this integral. So we need an upper bound for that integral. But remember that we proved here, I just erased, that gk was less than or equal to fk, right? This comes from the fact of the definition of gk, right? Let me recall that, or you can go back on the video to check this proof. But this is essentially due that for each fixed n, g and k, it's converging, so g and k was less or equal than fn for any n less than k, and fn was less than fk. So since gk is less than fk, this limit is certainly smaller or equal than the limit inf in k of fk d mu. Right, again, by monotonicity, we have that the integral of gk is smaller than the integral of fk. Therefore, the limit of this integral is smaller than the limit inf of this integral, and this is exactly what we wanted to prove. So it follows from these two inequalities that, in fact, the integral of fn is converging to the integral of f, and this proves the monotone convergence theorem. So let me just make a remark before we proceed. Here I'm assuming that fn is non-negative. Of course, we can prove the same result if fn is bounded below by a function g which is integrable. Right? If fn, the sequence fn, is bounded below by an integrable function, we can just apply we can just consider the sequence gn which is fn minus g, which is now a non-negative sequence, which is increasing to f minus g. Apply this result to this sequence, and then use the linearity of the integral to get rid of the function g. So we can extend easily this theorem to the case in which the function, the sequence fn, it's bounded below by an integrable function. Let me also use this result to observe the following. Well, let's now take a function f, which is always measurable and non-negative. And I want to use this function, which is defined on a measurable space omega f mu, to define a new measure, which I will represent by mu f, which is defined on the same measurable space, and which will be given by, well, if I have a set A in the sigma algebra f, I want to define this object as the integral of f on the set A d mu. Okay. So I'm defining this, this function, and what I claim is that mu f, it's a measure. And I will use the monotone convergence theorem in order to prove that mu f, it's a measure. Well, this is easy. If I take the empty set, it's clear that mu f of the empty set, it's equal to 0, because we have seen that the integral of any non-negative function over a set of measure 0, it's equal to 0. So this is a simple consequence of one of the properties of the integral. And then now, what's important is to show that mu f, it's a sigma additive. And this is where we will use the monotone convergence theorem. So let's assume that A is a set, and that A can be written as the joint countable union of sets AI. And what I want to show is that the measure of A is equal to the sum of the measures of AI. So, well, let's write that here. Mu f of A, by definition, it's the integral over A of f d mu. But A is the the joint union of the sets AI. So this, by definition, it's the integral over the set. So I'm taking the indicator of A, multiplying that by f d mu. Since A is the disjoint union, the indicator of A is the sum of the indicators. So of AI and now this function which appears here, it's in fact, let me define fn as this function which is obtained by taking the sum of the first n terms of AI times f. So this sequence fn, it's clearly converging to the infinite sum, which is the indicator of A, f. So we have here a sequence, fn, of measurable functions, non-negative, which are increasing to 1af. So by the monotone convergence theorem, the integral of fn, which is converging to 1af, it's the limit of these integrals. It's equal to the integral of the limit, but the integral of the limit, it's exactly this function, which is 1af. So here I'm just using the monotone convergence theorem applied to the sequence fn. Right? I have here a sequence of non-negative functions, which is increasing to this function, which is also that one. and therefore the integrals are converging to the integral of f. But what is the integral of fn? Well, by linearity of the integral, I can exchange the integral with the sum. So this is the limit of the sum of the integral over ai f d mu. Well, but this is by definition mu f of ai, and here the limit as n goes to infinity of this integral is just the countable sum of mu f ai. So this proves that mu f of a is equal to the sum, and therefore that mu f is sigma additive. So in this sense, we are, well, once we have a non-negative integral function, observe that I'm not assuming here that f is integrable, just that it's non-negative, we can define a new measure on this space with this integral. I want to make an observation about this measure. It's the following. Well, assume that we have a set B, such that, which is measurable, of course, such that mu of B is equal to 0. Well, we have seen that in this case, the integral of over B of the function f, it's equal to 0. Since B has measure 0, the integral of f is equal to 0. And this is exactly mu f of B. So if mu of B is equal to 0, then what we get is that mu f of B is equal to 0. And so this leads us to a definition of absolute continuity which is as follows. Suppose that you have two measures, mu and u, which are defined on a sigma algebra f defined on a set omega. I will say that mu is absolutely continuous with respect to nu. So if nu of A equal to 0 imply that mu of A is equal to 0. Right? So this example led me to this definition. I'll say that mu is absolutely continuous with respect to a measure nu. If whenever I have a set A which has measure 0 with respect to nu, then it has measure 0 with respect to mu. And I will represent this absolutely continuity by that symbol. So mu, it's absolutely continuous with respect to nu. And we have just seen in this example that if I have a function f which is non-negative, then the measure mu f, it's absolutely continuous with respect to mu. This is exactly what we proved here. If mu b is equal to 0, then mu f of b is equal to 0, which means that mu f it's absolutely continuous with respect to mu. And with that, we can anticipate a very important theorem, which is the Radon-Nikodym theorem, which tells you exactly the reverse result. So the Radon-Nikodym theorem states that if we have a measure mu which is absolutely continuous with respect to nu, then there exists a function f, or let me call it g, which will be represented by d mu d nu such that, well, mu of a set B will be equal to the integral over B of g d nu. Right? So the Radon-Nikodym theorem gives you the existence of this function f if you have a measure which is absolutely continuous with respect to another one. So if a measure mu is absolutely continuous with respect to g, to a measure nu, the Radon-Nikodym theorem tells you that there exists a function g which is non-negative, such that the measure of a set B can be represented as the integral of this function g on the set B with respect to nu. So this gives you, the Radon-Nikodym theorem gives you a converts to this observation that the function, the measure mu f, it's absolutely continuous with respect to the measure mu. So this will be proved in well, the next 2 or 3 lectures. And so maybe let me just give you an example of measures which are not absolutely continuous one with respect to the other. So let's consider a function, so in R. So let's consider a function f, which is, say, continuous and positive. So you have here your function f, and I will consider the measure mu f, which is the measure gives to the set A the measure A, the integral of f, which is that function on A with respect to the Lebesgue measure that we constructed. And then this is one. And then another point, another measure, let me fix a point x in R. And let me represent by delta x. So here is a point x. So delta x is what we will call the Dirac measure on x. So if you take a set B, the measure of B with respect to delta x will be either 1 or 0. 1 if x belongs to the set B, and 0 if x does not belong to B. So this measure is concentrated on one point, on the point x. If the set contains this point, it has a measure equal to 1. If it doesn't contain its measure, it's equal to 0. So you see, if you take the set x, it's clear that mu f of x it's equal to 0 because the set, the point x has measure equal to 0 with respect to the Lebesgue measure, and therefore this integral is equal to 0. So mu f at x it's equal to 0, but delta x at x it's equal to 1. So it's not true that delta x it's absolutely continuous with respect to mu f. Right? We just obtained a set such that mu f of x is equal to 0, but the x of this set is not equal to 0. So this is false. Right? Because if it were true, this means that whenever a set has measure 0 with respect to this measure, it will have measure 0 with respect to that one. But here it's an example of a set which has measure 0 with respect to that measure, but which does not have measure 0 with respect to that measure. So it's false that delta x it's absolutely continuous with respect to mu f. Now let's take a set, say an interval AB, which does not contain the point x. Now we have that delta x of the interval AB it's equal to 0. But if f is strictly positive, then we have that mu f of this interval AB it's strictly positive. right? Let's assume that f is a continuous function which is bounded below by a constant on this interval ab. And therefore, it's not true that mu f it's absolutely continuous with respect to dx, so this is false. Because here again, we obtained a set, the interval ab, which such that, well, delta x of this set is equal to 0, but it does not imply, well, that mu f of this set is equal to 0. It's in fact it's really positive. Therefore, it's not true that mu f is absolutely continuous with respect to delta x. So we have here an examples of measures which are not absolutely continuous with respect to one another, and therefore, well, you won't have this representation as in terms of a function. So last remark concerning this measure, it's about uniform integrability. So what I claim is that if you consider this this function, so now I want to tend to take sets A which have small measure to guarantee that this integral is bounded. So more precisely, what I want to prove is that for any epsilon positive, I can find a delta positive such that if mu of A has measure smaller than delta, then mu f of A has measure smaller than epsilon. So in this sense, that uniformly over the sets A with measure smaller than delta, I have mu f smaller than epsilon. The measure of A with respect to this measure mu f, it's smaller than epsilon. And so I need to estimate AF d mu. So I'll do that, I will cut this in two terms. One, I will consider the set of points in which f is larger than n. And the other point, it's the set in which f is smaller than n. There's f missing. So I just decompose my integral in two terms. One in which f is smaller than n, and the other one, the other piece in which f is larger or equal than n. So for this piece, since f is smaller than n, fn, I can replace f by n. So this second integral here, it's smaller than n. Once I replaced f by n, I can just ignore this indicator function and estimate this integral by the measure of A. While for that one, I can just ignore that we have A here and bound that integral by f larger or equal than n d mu. Now, if I assume that the function f is integrable, so let me assume here that the integral of f d mu is finite, I can rewrite this expression. Well, this indicator here can be written as 1 minus the indicator that f is smaller than n. I can use, since f is integrable, the linearity of the integrals, and to rewrite this first piece as f d mu minus f smaller than n d mu. Now, by the monotone convergence theorem, as n tends to infinity, this sequence of functions converge to f. Therefore, by the monotone convergence theorem, the sequence of these integrals is converging to that integral. Since this integral is finite by assumption, this sequence is converging to that finite number. Therefore, if I fix some epsilon positive, I can find some integer n, starting from which this difference is smaller than epsilon, say, over 2. So I just proved that for that fixed epsilon, I can find an integer n0 such that, which is finite, such that if n is larger than n0, then this first piece is smaller than, say, delta over 2. Epsilon over 2, sorry. Right, so I fixed epsilon, and I can find this integer n naught such that if n is larger than n naught, then this integral is smaller than epsilon over 2. Once I fixed this n naught, I can use here n naught and here n naught in this inequality. And now I can find a delta such that if mu a is smaller than delta, then n naught times delta will be smaller than epsilon over 2, and therefore this integral will be smaller than the sum, which is epsilon. Right? So this proves my claim, where I needed and I used the fact that f is integrable. Therefore, if the function f is integrable, we can show that we can make this family of measures, so we can make mu f a smaller than epsilon uniformly over all sets A, such that mu of a is less than delta. So now let's state the second main theorem, which is Fatou lemma. So this is also a very important result, which will be used many times. So again, I'm assuming that I have a sequence fn of non-negative functions, but now I'm not assuming anymore that this sequence is increasing or converge. It's any sequence of measurable, I always consider only measurable functions without repeating it, so any sequence of non-negative functions. And what I claim is that if I take the limit inf of fn d mu, so I have to take the limit inf because maybe this sequence fn does not converge pointwisely, that this limit inf is smaller or equal than the limit inf of the integral of fn d mu. And let me give you an example just to show that this inequality can be strict. That's a very simple example. You take the Lebesgue measure, and as function fn, you consider a function fn, which is equal to 1, say, if the point is larger or equal than n. So this is the graph of your function fn. So it's clear that the integral of fn it's equal to plus infinity for any n, while the limit of fn is converging pointwisely to 0, so the integral of 0 is equal to 0, and therefore we have a strict inequality in this example. So now let's prove this lemma, but the proof of this lemma, it's a very simple consequence from the monotone convergence theorem, because, well, let me define gk as the infimum for n larger or equal than k of fn. So gk, it's certainly a sequence of non-negative functions. It's increasing because here we are taking the infimum over a smaller and smaller set. So gk increases. And it's increasing, which is the limit? Well, it's the limit as k tend to infinity of this expression, just the limit inf. So gk is converging to the limit inf of fn. So what the monotone convergence theorem tells us? Well, it tells us that we have here a sequence gk. It tells us that the limit of this sequence, which is the limit inf of fn d mu, it's equal to the limit, so this is the limit of the sequence, limit, so this is equal to the limit of gk, right? So gk is converging to the limit inf of fn, so this is also the limit of gk. And the monotone convergence theorem tells us that this is equal to the limit of gk d mu. Right? So this is just the monotone convergence theorem. But gk is defined as the infimum for n larger or equal than k of fn. So this infimum is clearly less or equal than fk. And therefore, the integral of gk is smaller than the integral of fk. So this integral is smaller than the integral of fk, and therefore the limit of this integral is less than or equal to the limit inf of fk, and therefore we just proved that the limit inf, the integral of the limit inf of fn, it's less than or equal to the limit inf in k of the integral of fk, which is Fatou's lemma. So two observations. We required fn to be larger than non-negative. Of course, I can repeat the same observation, saying that, well, it's enough to require that fn is larger than g, provided g is an integrable function. And, well, now I want to state a result replacing limit inf by limit sup. So let's assume that we have a sequence hn, which is positive, and which is, negative. So this is hn, and let me write fn as minus hn, which is now non-negative, and let me just state what Fatou's lemma tells us in terms of hn. So I'm just replacing in this statement fn by minus hn. So the limit inf of minus hn d mu, it's less or equal than the limit inf of minus hn d mu. Well, now let's use the fact that if you take the limit inf of minus hn, this is equal to minus the limit sup of hn. So here I'm just saying that the limit inf of minus a sequence, it's equal to minus the limit sup of this sequence. And here I'm using the linearity to take out from the integral the minus sign, and then again using that the limit inf of minus something, it's equal to minus the limit sup. And here again, let's remove the minus sign, and let's multiply this equation by minus 1. So what I get is that the limit sup of hn d mu it's greater or equal than the limit sup of hn d mu. And this is what I will write here, is that we have a second result replacing the limit imp by the limit sup. We have that the limit sup of a sequence hn d mu, it's greater or equal than the limit sup of hn d mu. So this is what we proved, provided the sequence hn it's non-positive, it's negative. Right? So this is exactly what we proved here. So let me erase this proof and just keep the result. And as for the limit imp, we assume that fn was negative, and we observe non-negative, and we observe that it could be bounded by an integrable function. The same thing here holds. If instead of assuming that hn is negative, we assume that hn is bounded by an integrable function, we can just use hn minus g, apply this lemma, and then remove g by linearity of the integral. So here are the statements of Fatou lemma with lim imp, Fatou lemma with limit sup, and we will use these two statements in order to prove the next result and the last one of this lecture, which is the dominated convergence theorem. So let me state the last theorem of this lecture, which is the dominated convergence theorem, which can be stated as follows. You consider a sequence fn. Assume that this sequence fn is converging to f, and that this sequence fn, its absolute value, it's bounded by a function g, where g is integrable. Then the claim is that f, it's integrable, and fn d mu converge, the integral of fn converge to the integral of f. Observe that fn it's integrable because the absolute value of fn is bounded by an integrable function, so we know already that fn is integrable. And what this theorem is saying that, well, f it's integrable and the integrals of fn are converging to the integral of f. So let's prove that. And in this proof, we will use Fatou's lemma 2 times. Well, on the one hand, it's clear that f is integrable because since fn is converging to f, we have also that the absolute value of f is bounded by g, which is an integrable function. So it's clear that f is integrable. And now let's use Fatou. So let me start with the limit sup. So you see that fn it's less or equal than g. So it's true that fn it's less than g, which is an integrable function. So we will be able to use Fatou with non-negative functions, but it's also true that fn it's larger than minus g, and minus g is integrable, so we'll be able to use both the limit imp result of Fatou and the limit sup of Fatou, either by using that inequality or by using this inequality. So Fatou tells us that the limit sup of fn d mu it's less or equal than the limit sup of fn d mu. Right? So let me just recall that here we are using fatu. So let's go back to the previous board. So in this first step, I'm using that limit sup of fn, which is now replaced here by hn. The limit sup of fn, it's less than or equal than the limit sup of fn, because fn is less equal than a function g. So since fn is less or equal than g, we can use fatu, as I said. Now the limit sup of fn, since fn is converging to f, this is just equal to f, which is also equal to the limit imp of fn d mu. And now we'll use the second inequality given by Fatu's lemma, is that the limit imp, it's smaller than the limit imp of fn d mu. So this is the second, the first inequality we proved in Fatu's lemma, and we are allowed to use that because fn is greater or equal than an integrable function. So let's go back to the previous board to check that. Right, what I'm using now is that the limit imp of fn d mu, it's smaller than the limit imp of the integral of fn, because fn is bounded below by an integrable function. So this justified that inequality, and if we observe that, well, this is the limit imp, it's clearly less than or equal to the limit sup of fn d mu. Therefore, we started with something in sequence of inequalities and we end up with the same object. Therefore, everything inside it's equal, which means that the limit sup, it's equal to the limit imp, which is equal to f, and therefore we just proved that this sequence is converging, and it's converging to the integral of f, and this is the dominated convergence theorem.